training we're doing and retraining, the platforms we're creating, PXI, Compact Rio. These platforms go, if you look at the PC bus, it's changed roughly on a decade timeline and in a fundamental way. So we do the same thing, follow that plan. At the 5-year level, you're talking more about what's hot. Unfortunately, right now in test and measurement, not too much is hot, right? I mean, but basically, you try to find those things that are doing better and focus on those a little bit more in that 5-year timeline. Goals that we're setting roughly in that timeline, quality goals as we've stepped up our very critical role in with our customers. 1 year is more about the sales forecast and deploying goals to each individual. And then, as I always put it, we hope that this longer-term thinking is making it possible for us to just add up the numbers and publish them. But in reality, you always have to scramble a little bit. But that's kind of the philosophy that we're trying to create in how we operate. Now, as was mentioned, we have been on the Fortune 100 list now for 14 years running, and then most recent, the last 2 years on the world's best multinational workplaces, great place by the Great Place to Work organization. So this is we take a lot of pride in these that we're able to. I always say you have to be a good business to be on these lists, because the minute you have to start laying on people, the culture starts breaking. So to me, that's always been a motivation to be a good business. Now, I mentioned our timelines, our vision were roughly decade timelines. This first decade was really about self-financing. We moonlighted while we finished up a pretty massive project at the university. And then the second decade, we had just introduced LabVIEW, and we continued to work with the GPIB, which was this instrument interface. The IEEE 488 is more formal name for it, HPIB. And then with LabVIEW and data acquisition, we would set the stage for next level where we actually started making measurements with our product. And then the third decade, we started adding automation in, and then these system-level products, and that would take us the next level up the curve. And now in the fourth decade, we use the phrase graphical system design. And while I'm not talking about today that much, cyber-physical systems is another term being used, and also the Germans are using in their Industry 4.0 working group, they call them the Industry 4.0, the next revolution, where you're talking about computers used with physical systems. So it's basically includes test and measurement, interestingly. So this is a slide I presented in 1983, where we talked about the benefits of a GPIB system. And really, in the end, when I look back, I used these just recently, this slide recently, it was set the vision of what we would do for the next 3 decades. We were always to these goals of automation, faster, handling data better, more reliable, better, so forth. And really, for 3 decades, we've pursued this vision that we outlined back in 1983. To do that, we worked with Jeff Kadowski, one of the co-founders, came up with LabVIEW for automating GPIB systems, where we introduced the term virtual instrumentation. So Jeff and I worked for 2 years trying to figure out a system design tool that would really match this problem to do for test and measurement what the spreadsheet did for financial analysis. And to this day, nobody has found a better answer to that question. It really effectively was a programming language that used data flow which happens to work very well with distributed systems, with multi-core and FPGAs, as we'll see. So this is a slide I use sometimes to show the evolution of instrumentation, starting with general radio at the vacuum tube for the first 45 years of modern instrumentation, then moving to Hewlett-Packard for the next 45 years with the transistor and microprocessor. And then we would claim the next 45 years is about software-based systems. And we see it in every area. We see it with smart mobile devices. We see it with PCs. And so why not instrumentation as well? So our perspective is that instrumentation will move to a software-based view, and we're using our products to do that. So here we see a typical way these automated systems work. We have card modular components that do I/O, both input and output, with digitizers and D to A conversion, and then the software to integrate it. And a PXI system typically can get up to 10x improvement in performance, and I'll show a specific example to show that. Because of the better synchronization of the measurements in the system. Now I'm going to switch topics and talk about a watch. And we see a picture of supposedly the first watch. And so then I asked the question, how many of you are wearing a traditional watch in the audience? Quite a few, right? A lot. So, and then how many of you are wearing the virtual or the alternative watch? About the same people, right? So we both have the traditional instrument, and the watch or clock is an instrument, and then we have the new virtual instrument or software-based one, right? So why do we have both? Well, this is kind of turned into jewelry. I kind of feel like Linus with his blanket. I got to have one of these. And this is, we know this is probably more accurate, right? Because it's synced up with cheap, global time and all this good stuff. So basically, there's a transformation taking place. So let's look at instruments. Here we have some instruments on one side, and then we have physical embedded systems on the other. Things like a television and a calculator and things like that. A device, a CD player. And so moving on, these things all now have their virtual or software-based alternatives. We've got the virtual instruments. We have even a level on your iPhone. And then one that I'm really fascinated with is, I was recently watching some bagpipers, and they were tuning up, and this guy was walking around with his bagpipe tuner tuning the bagpipe. And, I didn't know a bagpipe could be tuned. So I was curious, is there this equivalent on the iPhone available to do that, Sure enough, for $24.95, you could get a bagpipe tuner. So the poor guy making bagpipe tuners now is in big trouble, right? And along with guitar tuners and a lot of other things, the world has just shifted on us. And then on the other side, we have the platform-based embedded systems building the same things we saw, television, a little tiny television. The kids don't seem to mind. That's tiny. And all these other things that are embedded systems. So, in fact, one platform is doing both. It's doing instruments, and it's doing embedded systems. So that was an observation we made some years ago. Matter of fact, one of the first customers was somebody trying to control a giant engine that was burning waste gas off of a waste dump. So we've been in the embedded systems business for many, many years, and recognizing that made us realize we need to think about that side too. So if you look at, there's a bagpipe tuner now that's available on the iOS. and along with almost a million other applications. So this platform has revolutionized a whole bunch of things, a whole bunch of businesses, and understanding that and how the software plays and which things are vulnerable to that is important in the process. So, okay, how did we get where we are? Well, looking in the rear view mirror, we're not the only ones who've been looking at this problem from this perspective. Berkeley invented SPICE. The two spin-outs, Cadence and Synopsys, are the leaders in chip design. The next thing on their list was data flow for programming systems. And they've been working on it. Professor Lee, Edward Lee, got his PhD in 1986, same year we introduced LabVIEW. So this system design approach isn't just unique to NI, but I think we're the only company that's ever really made a business out of this approach. But it is built on very fundamental computer science. So if you look at our platform now, we literally have hundreds of thousands of applications, tens of thousands of embedded systems, building these systems this new software-based way. And many, many different applications, all the way from alternative energy to smart grid analyzer, controlling wind turbines, as well as traditional test and measurement. And one of the advantages a platform gives you is scale. You get a lot of volume, so you get a lot of scale in how you operate. So for us, that's been a very important point, building on a platform and then having, just as the iOS has a choice of hardware that meets customers' needs, we have our hardware platforms that this software runs on to create the platform. And it's all about abstraction, being able to do things. One application we did, 2 guys part-time in a couple of months did what was going to set to take 600 DSP programmers. So the scale of what can be done in some cases is quite dramatic, as is proved by things like the iOS, which has almost 1 million apps. Can you imagine how much labor went into the products that went before? Probably a few orders of magnitude more than the 1 million that were created for the iOS. So the other trick is to work with other tools so that you can integrate into design environments, into Mathematica, modeling tools like Modelica, software for RF design and so forth. So you play in an ecosystem for building your products. Now, another way to look at it is this way, where you traditionally had this group of experts that would come together. And this required a critical mass, a big investment, and all the right experts to show up at the right place at the right time to build these systems. You had to have hardware designers, software designers, maybe ASIC designers, all these guys. Well, with the platform-based, you start with that platform and build on it. And then the domain expert becomes the major player in the system. This is often mechanical engineers now that can do that. And with a system that built around a platform-based approach, and of course you still got to hook up the sensors and all the other things to the real world, but you have a much simpler, faster process, whether it's building a test and measurement system or whether it's building industrial embedded systems. So, and then if you need to go to high volume, you can go back and scale back, use that prototype where you learn and prove that all the algorithms are correct, then you can move back to high volume with custom